So, good morning, everybody. Today we're going to be doing lesson 4, which is talking about electrical energy, but now in terms of circuits, which is what we use on a daily life. So, let's review the story so far. Over on the right, you see all the equations that we've learned so far, and we've learned that energy is conserved, and we can use that conservation of energy by first knowing how to calculate the electrical potential energy. And then we know that that electric potential energy can be transferred to other things. And some of the examples that we've done so far is moving that into kinetic energy. So having some charged object that has an electrical potential energy, then converting that to kinetic and finding out how fast it's going. But we can also use that electric potential to do work, and that's what we do most of the time. I am talking to you on my laptop right now, which is using that electrical potential energy in order to do work. In this case, power all of the various different circuits that allows you to hear and watch the recording. But one of the things that we've been running into is the charge of the electron is tiny. 1.6 times 10 to the minus 19 coulombs. So the energies that we've been dealing with are similarly very, very small. All of the problems that we've been doing have been full of scientific notation where the exponents are times 10 to the negative big number, and it's really, really small. And really annoying to be using all of those scientific notations because we're dealing with really, really tiny stuff. So, in order to have more useful numbers, the kinetic energies have been tiny, the potential energies have been tiny. There's no way that we could use that to do useful things energy-wise in the world we live in. So we're going to need much bigger numbers. We're going to need much bigger charges. So we're going to be now using a full coulomb as our unit of charge. And let's talk about how we're going to do that. If you'll pardon the pun. Having an object with a coulomb of charge is really hard. So if you were to take a metal sphere, like say a Van de Graaff generator, which is the metal sphere that you put your hands on and all your hair stands up, if you have hair. 100 microcoulombs, so 100 millionths of a coulomb, is actually a really high charge for one of those. Much more than that, and now it's not going to be possible to charge it up anymore. So, yeah, we're dealing with, there's a limit to how much charge we can put on an object, and that limit's really small. And electrons have a charge of 1.6 times 10 to the minus 19. So, you could start adding electrons, but you need to add a bunch, and then they all start to repel each other, so you're not going to get big charges. So you need to have 6.25 billion billions of electrons. So that's 6.25 times 10 to the 18 electrons in order to have a coulomb of charge. And there's just no way that you can pack all of those into one spot before they just start repelling each other and flying off someplace else. But what you can do is electrons have no problem being in, say, a neutral hunk of metal. And metal, as you might remember from chemistry, is a conductor, so you can get them easily to flow down a wire. They're not congregating in any places, so they're not going to build up a charge any place and repel at everybody to keep them from moving. So yeah, this is going to work for us because we can send now a large amount of charge down a wire that isn't building up anywhere, so it's going to keep flowing. So, and this flow of electrons is called current. And the definition of current is the amount of charge flowing through something, a wire or something else, every second. And for the most part, the examples we're going to be doing is wires. All right, so if we were to put that in an equation, we would come up with this. So I, and that's going to be our symbol for current, is going to equal charge, and you might remember that our symbol for charge is Q, over time. So the reason why I is the symbol of current is because in the early days of electrical circuits, it was called intensité. And if you don't like that, blame the French. So let's talk units for a moment. So the unit for current is amps, and that's short for ampere. Now you know the name of the Frenchman that you should blame. So 1 coulomb of charge every second is going to equal 1 amp. So 1 amp is going to be 1 coulomb of charge flowing through a wire every second. So that means that through all the wires that are pulling 1 amp, like the ceiling fan above me, so the lights on that ceiling fan actually are pulling almost exactly 1 amp, which means that 6.25 billion, 6.25 times 10 to the 18 electrons are flowing through that fixture every second. So, another bad pun, but we'll go with it. So, we know that work is voltage times charge. So this is one of the equations that we saw above. That's the potential energy of an electron. So if you're moving from a potential energy, the electric potential energy, and making that do something else, it's the change in energy of the system. So that's going to be the work of the system. So the work that one charged object can do is equal to the charge of that object times the voltage. That's also equal to the change in electric potential energy. We know that work, or power, is work over time. So power is work over time, and that means that power is also charge times the voltage over time. And we also know that charge over time, that flow of charge per unit time, is also called the current. So this gives us a new equation. The power flowing through that light is equal to the current times the voltage. So if we return to that light as our example, what we can figure out is that the voltage is 120 volts because it's hooked up to the wall, and the walls are all about 120 volts. So the current, I said that was 1 amp earlier, but how did I know that? Well, I can look at all of the light bulbs in there and see that there are 3 40-watt light bulbs. So with 3 40-watt light bulbs, that's 120 watts. 120 watts divided by 120 volts gives me the current of 1 amp. So let's do an example problem. So a cell phone battery provides 3.82 volts, and when fully charged stores about 27 kilojoules. So I believe that the numbers that I found for this problem are for an iPhone 7, but I don't quite remember. So if it can play TikTok videos for 6 hours, oh dear, the old teacher is trying to sound cool by using buzzwords. Before the battery dies, how much power did it use? So let's figure that out. So power is work over time, and the work that we're going to be using here is going to be that change in energy. So we need to take that change in energy and divide that by the total time. So 27 kilojoules. It's 27,000 joules of energy that this battery can hold. And it's going to be using that over a period of 6 hours. So that's going to be 6 hours times 60 minutes in an hour, and then times 60 seconds. So when we do that math, we end up with the cell phone only using about 1.25 watts. And it should be mentioned that this is how long it would last is strictly an estimate on my part. But we're not outside the realm of reasonableness. So you might be looking at this and going, that cell phone's only using 1.25 watts, but that light fixture was using 120 watts. Why is that using 10 times more electricity than the cell phone that I have in my hand? And the answer, quite simply, is that my light fixture is using incandescent light bulbs, which are horribly inefficient. Your cell phone uses LEDs, which are much more energy efficient. So that's why when you go up and try to change a light bulb that just burnt out, it's really hot because it's losing a lot of that energy. It's wasting a lot of that energy as heat. Whereas your cell phone, unless you're using a whole bunch of energy, doesn't actually get hotter. So let's look at current. So we know that the equation for power is the current times the voltage. So we know the voltage, we know the power. So let's go ahead and solve for current. So current's going to be the power divided by the voltage. I can now plug some numbers in. So 1.25 watts, that's what we found earlier. 3.82 volts, that's what the battery is providing and what I was able to read off the back of a cell phone case. And we can then do this math and find out that our answer is 0.327 amps. But what is that in electrons per second? So we know that 0.327 amps would be 1 amp is 1 coulomb per second. So 0.327 amps is going to be 0.327 coulombs every second. And 1 electron has a charge of 1.6 times 10 to the minus 19 coulombs. This means that 2.1 times 10 to the 18th, so 2.1 billion electrons are flowing around the circuit in your cell phone every second. So, hopefully, this allows you to now appreciate some of the things that are going on and in the circuits that you use on a daily basis, and now see how the stuff that we've done prior, so how the stuff that we've been looking at so far with how energy is used and how energy it works on the very small scale can now be scaled up, and in talking about billions upon billions of electrons working together, we can now use that, we can now harness that in order to power everything in our daily lives. With that, I wish you the most excellent of days.